Hi, welcome to lesson 8.02. Here we're going to deal with some AP free response questions that deal with motion and that you can use a calculator on. And the trick here is balancing using your calculator but still showing your thought process in your work and justifying your answers appropriately. Let's get started. So before we dig in here, I want to very briefly go over 4 simple keys to success that will help you maximize the number of points that you earn on each of these problems. The first is, of course, to recognize what it is you're trying to find. Now, sometimes this is very straightforward and sometimes it's not. And let me give you an example. Sometimes the question asks you straight out to find the mathematical, something or other. Find the value of the second derivative when x equals 2. Something very simple like that. Or it will be a real-world application problem where it'll ask you a real-world question. And in those situations, you want to make sure that you translate what they're asking you into language that you can clearly understand. And this usually means translating whatever you're trying to find into the simplest mathematical form you can. Mathematically, what is it that I'm trying to find? Once you've recognized that piece and you've done the translation, you then want to have a plan of attack, right? What are you going to need to do in order to find it? And this boils down to the sort of crux of everything else, which is what will guarantee, what steps can I take that will guarantee I'm able to find this piece of information? And it really goes to then the justification piece, which we'll talk about in a second. But this here is saying, what is your plan going to be? What do you have to do to find that piece of information? And whether you have written your plan out beforehand or if you feel very confident, so you simply come up with your plan internally in your head, you're then going to show that your plan, what your plan of action was, with your work. Okay, so this is the piece that's very important. Your work should clearly illustrate your thinking, right? What was your plan of attack? So if I'm just reading through your work, I can see your plan taking shape. And so whether you have a calculator or not, you really want to be showing all the steps that you are taking. You want to set up your definite integral, you want to set up any differentiation you're doing, I'm taking the derivative of this. Don't just leave that out, show that work, because oftentimes you'll get a point or two simply for showing that you wanted to take the right steps, right? That's half the battle. So you want to make sure that you are showing all your work and that it is a clear process. Someone can understand your thinking. It shouldn't be scattered all over the page. All right, thirdly, your justification. You're going to get a point for justifying that your answer is correct. And so what you need to do is essentially answer, why does my answer have to be correct? Logically, why is this true? And so this gets back to your plan that you came up with, right? Your plan should have been a bunch of logical steps that said, okay, if I do these things, then I'll know that this is the correct answer. And so you want to succinctly and clearly explain this to the reader of the problem, right? And we'll obviously do a bunch of examples where we go over this justification. This is a piece that is always worth a point and that is often hard to attain, but we're going to work on it so that we get it every time. And lastly, you cannot forget units. You're going to get a point for having the correct units, and so no matter what you did wrong leading up to it, there should be no excuse for getting the units correct. Oftentimes you can simply look back to what it was you were trying to find in order to make sure that the units you've written there make sense. And we discussed this previously, but I can't overstate it enough. You want to show all the integration and differentiation or any other move mathematically that you make so that you are illustrating to the person reading the problem, look, I knew what I needed to do, so even if I made a computational error along the way, at least I should deserve some points for having the correct plan and the correct logical method for finding the answer. Okay, so always have these, you should have these written down and just kind of look back at them as we solve a bunch of these AP free response questions going forward. So with that being said, let's get to it. All right, so the first problem we'll do is 2007. First and foremost, we're going to be cutting down the number of problems we do, and we're going to be focusing on some more rigorous problems from the AP test. So it is worth your time to copy this question down. It will help you internalize the information and get used to the way that these problems are written. So pause the video now, write this down, include the graph, take note, of course, of the axes here, and then once you have a copy down, press play, and I'll take you through how we're going to work this one out. Alright, here's what you're going to do. You're going to set a timer for 15 minutes, and you're going to first read through the introduction, okay? Annotate any key pieces of information, write down any key pieces of information that they give you here in the problem, and then begin. For each part, obviously starting with part A, identify what it is you're trying to find and come up with a plan of attack. Okay? At first, this is going to take a lot longer than 15 minutes. That's totally fine. You're just setting a 15-minute timer so that you get an understanding of sort of where you're at when those 15 minutes are over, so you can track your progress as we move along. Remember, it's currently January. We're taking the test in May, so there's no the timing piece will come with that. Don't worry about it. So 15 minutes, and go through what am I trying to find, what's my plan of action, then carry out your plan of action, have your solution, include units, and write out a justification if you need. Remember, you have a calculator on this problem, so part of this is writing out what you're doing and then sometimes actually doing it with your calculator to save you a lot of time. Okay? So go ahead and try this on your own first, and then see how long did it take you, where'd you get after 15 minutes. Press play, and we'll take a look at it together. Okay. I want you to draw a little line horizontally across your paper where you finished off at, and then you're going to want to take some notes based on the solutions we have here, because what you're going to do is we're going to actually score what you came up with on your own, so that no matter how low or how high it is, you can see your progress as we move forward. Key pieces of information that I noted: t can be greater than or equal to 0. That makes sense. Here's my velocity function. I'm going between 0 and square root of 5 pi. It's important. And that x of t is the position of the particle at time t, and that I have an initial position of 5 on the x-axis. So for part A, I am trying to find the acceleration of the particle at t equals 3. Pretty straightforward. I know what I'm trying to find, acceleration, when t equals 3, and my plan is straightforward. I know that the acceleration is the derivative of velocity. So that means that the acceleration at time 3 is going to be equal to the velocity, the derivative of velocity, at time 3. Now, I can take the derivative here by hand, and that wouldn't waste too much time, but you have a calculator here. So it makes a lot more sense to find the derivative at t equals 3 using your calculator. So what I like to do is graph the function and then use the second calculate option to take the derivative at an input value of 3. So you can go ahead and do that. If you did this by hand, the derivative of sine of t squared is going to be 2t cosine t squared. And so when I input 3, it's going to be 2 times 3, or 6, times the cosine of 3 squared, or the cosine of 9. And so this is the part that you may not include if you just simply went straight to your calculator. But from here, regardless, you're going to evaluate with your calculator. Make sure that you're in radians, of course. And you're going to get a value of negative 5.466 or 4.567 if you rounded. Notice here the important pieces are that I'm showing my thought process. The acceleration at time 3 is the derivative of velocity at time 3. If I did that by hand, I can show that work here. However, I could have just gone straight to my calculator and evaluated the derivative of this function here at 3. And there's my solution. Part B is pretty straightforward. I want to find the total distance traveled by the particle from time 0 to time 3. And I know, of course, that total distance is a little different than displacement in that I want to treat distance that it travels to the left and distance it travels to the right all using the same value, all is positively influencing the total distance. So I'm going to take the definite integral from 0 to 3 of the absolute value of my velocity, and that will give me the total distance. So I need to set this up, that's my plan. I need to show my plan here with my work. So here's what I'll say. So here I have total distance. I'm saying what it is I'm finding, and that is going to be equal to the integral from 0 to 3, my time interval, of the absolute value of velocity dt. Now here's where having a calculator probably saves you 10 minutes of work. Using my calculator, I can evaluate this definite integral because I can input absolute value signs in my calculator. If not, and I had to do this by hand, what I would be doing is going and finding where the velocity function is negative, essentially making a sign chart for my velocity function between 0 and 3, so that I can then integrate those parts separately. And that's going to be no fun whatsoever. However, your calculator has the ability to take the absolute value of something and to evaluate a definite integral. So when you're inputting your function into your calculator, you can put absolute value brackets around your function. To do that, simply use math. So if you hit math, and then if you scroll to the right to where it says NUM or num, the first option there is ABS, which stands for absolute value. And if you hit enter, it will then put absolute value brackets into your current situation. So you can take you can use fn int and then use the absolute value brackets around your function when you're inputting your function sine of t squared. And when you do that, you can then compute the value of this definite integral very quickly and find that it is equivalent to 1.702. And that is the total distance traveled by the particle between 0 and 3. Notice how much easier that is going to be. Okay, part C, very straightforward. Find the position of the particle at time t equals 3. And here, my planning process should go, oh, I remember, I've done this a million times before. I have the velocity. I know that the displacement of a particle, in other words, the change in position, is simply the integral of velocity over that time interval. And if I have an initial condition, in other words, I know where the particle is at some point, in this case 0, then I can add that displacement to that initial position, and that will give me the position at any time I seek. So writing that out in general here, what I'm saying is that I can find the position at any time t by taking the initial position, in other words, a position at some time a, and then adding on the displacement, in other words, how much has the position changed between a and t, by computing that definite integral there. So here my work should look like this. I'm going to be finding x of 3, which is going to be equal to the position at time 0, so x of 0, plus the displacement between 0 and 3, which can be found, of course, using the definite integral. Alright, now I know the position here. I wrote x of 0. You could have just put in 5 right off the bat, but I wanted to make it very clear where that's coming from. And regardless, you would get to this point where you now have 5 plus this displacement, and it would look like this. Now I can, of course, compute this definite integral in my calculator. Don't want to do it by hand. Much easier to do this in the calculator. And when I do so, and I add 5 to that displacement, I'm going to get a value of 5.773, or if you rounded, 5.774, and that is the position at time 3. Part D actually involves a little bit more work, but shouldn't be any more challenging as long as you think about it and utilize the graph that we're given here. So we're trying to find, on the interval from 0 to square root of 5 pi, the time t where the particle is furthest to the right. And interpreting this mathematically, what we're thinking to ourselves is, okay, we need to know where the position function, x of t, has its greatest value, absolute maximum value. And so we know that we're on a closed interval from 0 to square root of 5 pi, so we can consider the endpoints and all of the points in between, the critical points, where the velocity changes from positive to negative, so where the particle switches from moving right to moving left. And if we consider all those points, we'll have all the possibilities for where the particle could be furthest to the right. In other words, I'm just employing my closed interval test, but notice I can just look at my graph here and sort of notice a couple of things. The velocity is going to be 0 at all of these points here, but I only need to consider the ones where the particle is moving to the right and then switches to the left. So here, this would not be a candidate because the particle is moving to the left and then goes moving to the right, so that's not going to be a candidate. This will be a candidate because the particle is moving to the right and then moving to the left. This won't be a candidate, and this will. So what I want to do is find those values, okay? And I want to explain why I'm doing this, right? I want to state that the particle will find its rightmost position when it is changing from moving to the right to moving to the left. In other words, where the velocity is equal to 0 and it was changing from positive to negative. And then, how am I going to actually find that? Well, you could go ahead and set your velocity function equal to 0 and solve for all those values. You could absolutely do that. It's not that hard. We'll talk a little bit about how we do that. But we have a calculator on this question. And so if we can just graph this function on our calculator, we can actually find all of these critical points and then use them to evaluate the position at those points. So let's go ahead and write out our introduction where we just say, look, here is how we're going to find them, and this is why we know we only need to consider these points. So writing it out, we consider the endpoints and all times t where the particle switches from moving right to moving left, which occur when v of t is equal to 0 and changes from positive to negative. And then we're going to go ahead and find these points. So these points occur when, and we're going to state them in a second. But we can visualize these pretty clearly, right? We're looking for where the velocity is 0, namely, those are these points here, and where it's switching from positive to negative. So the only points we're actually looking for are the t value here, here, and we already know this one here, and we know the left-hand point as well. Now, we can just go ahead and graph our function in our calculator and identify these points using the 0 function in our calculator. But we could do this in our heads pretty quickly also, and I just want to take you through that because this is a valuable little piece of practice here. I want to know when sine of t squared is equal to 0, and so this boils down to me saying, okay, well, where is sine equal to 0? And that's an easy thing to go about finding. So, of course, sine is equal to 0 at 0 radians, at pi radians. And remember, I need to consider t values. Well, t is being squared here. So obviously, what do I need to square to get 0? That's just 0. What do I need to square to get pi? Well, the square root of pi. So if I'm making a list of these t values, I've got 0, I've got the square root of pi, and continuing on, look, I know I'm going to go to 2 pi. Well, that means I'm including the square root of 2 pi because I'm squaring my t value. And then continuing along, I'm going to then go, okay, well, also at 3 pi, so that's going to give me the square root of 3 pi. Continuing along again, so I've gone around once, 3 pi, again at 4 pi, so that gives me a t value of the square root of 4 pi. And then again, finally at the square root of 5 pi, okay, which would be back here again. And I can do that in my head if I need to, or I can draw this out. But again, we have a calculator here, so let's use it. And graphing this on my calculator and finding the t values for these two intersection points, I find that this is going to be the square root of pi. Right? This here would be the square root of 2 pi. The next one comes square root of 3 pi, so that's the other one that I want. It's the two that I want. This would be the square root of 4 pi, which I don't care about, and this would be the square root of 5 pi, obviously. So I will write in my solution here, this is when t is equal to square root of pi and the square root of 3 pi. So now at this point, all we need to do is compare the position at all of these points that I've identified, at 0, at square root of pi, at square root of 3 pi, and at square root of 5 pi. And in part C, remember we found the position at time t equals 3. So we know the method by which we can find the position at any time. And so now I'm just going to test all of these times out. And instead of writing that out for every single one, I'm just going to say in general how I would find the position at any of these times, and then just do those computations in my calculator and write them out in my explanation here. And so here I have this written out. The position at any time t is given by this function here, x of t, which is simply 5 plus the displacement between 0 and t. So using all the points that I said I would consider, I have 5 as my initial position. Square root of pi, which if you found on your calculator, you'd get 1.772, gives you a position of 5.895. At the square root of 3 pi, which is 3.07, I get a position of 5.778. And then again, at square root of 5 pi, here I get 5.752. And so clearly I can identify that the absolute maximum value of my position, or when my position is furthest to the right, is at t equals 1.772. So that would be my conclusion. I've given wonderful justification, and just to make sure that I'm super solid in believing my answer, notice that this amount of positive area here appears to be much greater than any of these over here, and so it should make sense that after completing this portion of my trip, the particle is going to be furthest to the right, and sure enough, it is. Alright, now that I've written that out and you've seen us go through one together, we'll take a look at how the point breakdown goes for this question in class tomorrow. But in preparation for that, I want you to try one more on your own. So let's go ahead and take a look at that one. Alright, here we go. So this is from 2005. You want to go ahead and copy this question down in your notebook and then answer each part. Set a timer for 15 minutes after you've copied it down, and don't stop when the timer goes up. Just note where you were at, just so you can see your improvement over time. And don't feel rushed. Don't worry about making it in the time cap. Go through and find out, what is it that I'm looking to find? What is my plan? Write your work out, erase it if you need to, and rewrite it. Really focus on having your work look nice and getting all the points that you possibly can. And then we'll go ahead and we'll score both the problem that we just did and this problem in class, and then we'll try another one.